Oh, Sarah, good start. Dear ladies and gentlemen, first I would like to thank everyone who is willing to cooperate with us, who is friendly towards us, and has good intentions, and who also understands all the leaders that, and I think there are many of them, who understand that we want to build somehow different world, a better world, a more peaceful and prosperous world, and that the times are different. We now have this social media and we see around the world what is going on, and we see each other and we see that we are different but also very much the same. And there is only, I think, one obstacle that we need to do toward this, and I think we are doing pretty well right now. I'm very positively surprised, and I must say great thanks to our engineers, very good, and scientists who made all those weapons. I saw how the things work, and really good. And I don't want to be clever here and say this, but you know what to do. Just keep on developing and keep on finding protection for the same products that you do, because you never know when they will come from the other side. And yes, just keep on, and I think we will expect even more weapons that will come, I hope, but for now this goes good, and it seems it will go on for quite a while, and that's why it's very important that we need protection as well. By the way, by drones, I also thought maybe you will do reusable drones, more sophisticated, more expensive ones, which could be sent back and back again to the battle and with bomb. But another important thing is also a shield. We need a shield, and I was thinking about that, and I came to the idea, and that idea is as follows. If you have only one shield that has a success rate, say 60%, 0.6, then it's 60%. But if you have three such systems, then the probability of success is calculated 1 minus, now in brackets, 1 minus p, which is success of 1, and close the bracket to the power of 3 if you have 3 such systems. And if only 60% is success of one system, 3 altogether, which is parallel, they're connected, not sequential, you will get more than 90% success rate. And the idea is this, that we form 3 groups, international, for different countries, different people, but be careful not to have spies among them, check them, and that they would each build its own system, and then they will integrate them together. And the point is that the system is built as fast as possible, as cheap as possible. It must be very cheap, and at least 60% of success rate. And of course, very light. I see these Patriot systems are good, but are quite heavy. And here, yes, I would also like to say that in Europe, I said before, I suggested that we would send, if USA requests our help, I think we are obliged to send them something and to allow bases to them. And here I would really like to apologize to USA, and I think and hope that Europe, if the next time, I hope will not be necessary, but if it will be the next time, that we will engage and help USA, because USA has troops here in Europe, has bases, and it has nuclear weapons that we can use whenever we want. We get planes from them, protection. So I hope you agree with me that next time we'll be acting differently. So today, first we will have some economics. My goal is that actually whole world becomes developed, that we all develop. Only thing what is bad is the more developed you are, the more you are polluting the environment. So we need to learn how to recycle things, and how to not to cause the warming of the planet. So yes, of course, we need to develop the world, but we need to develop it sustainable. So today something will be about economics, some biography, then we will calculate something, say something, and then follows Tensor Algebra, our 5th lecture, I think. So let's get started. So let's continue with our course of economics, and later I think it will come to computational economics, and from today on We will start to do also computer programs in Python. It's free, so you will be able to use it by yourself, either on computers or on the phones. It works as well. And I will be giving you these programs, so you will have a chance to learn. So, David Ricardo, 1772 to 1823, was one of the most influential classical economists in history. Alongside Adam Smith, he helped shape modern economic theory. What makes Ricardo fascinating is that he wasn't an academic, he was a widely successful stockbroker who took up economics as a hobby in his late 20s. Ricardo was born in London to a Sephardic Jewish family of Portuguese origin. His father was a successful stockbroker. At age 14, Ricardo entered the London Stock Exchange with his father. However, at 21, he broke away from his family, converted to Unitarianism, and married a Quaker, Priscilla Ann Wilkinson. His father disowned him. Forced to strike out on his own, Ricardo started a brokerage firm. He proved to be a financial genius, amassing a massive fortune. His biggest financial win came from speculating on the outcome of the Battle of Waterloo in 1815, effectively securing enough wealth to retire in his early 40s. That was also my goal, but now I started to work widely. While on vacation in 1799, he boldly picked up Adam Smith's The Wealth of Nations and became hooked. He began publishing articles on monetary theory, culminating in his masterpiece on the principles of political economy and taxation. Ricardo purchased a seat in the British House of Commons. He used his position to advocate for free trade. He died suddenly in 1823 at the age of 51 from an ear infection that spread to his brain. David Ricardo was a fierce intellectual rival with Thomas Malthus. They disagreed on almost every major economic issue of their days, yet they shared one of the most famous, respectful, and warm friendships in the history of science. They were engaged in a non-stop war of ideas. Malthus was a college-educated clergyman who looked at the world with pessimistic anxiety. Ricardo was a self-made Jewish-born stockbroker who viewed the world with analytical optimism. Their arguments fundamentally shaped the trajectory of classical economics. Glut theory vs. Say's law, the cause of depressions. Malthus argued that an economy could suffer from a general glut, a situation where society produces more goods than consumers want or can afford to buy, leading to mass unemployment and economic stagnation. He argued that the rich save too much money instead of spending it. Ricardo, the equilibrium believer, strictly defended Say's law, which states that supply creates its own demand. He argued that the general overproduction of goods was mathematically impossible because the very act of producing a good generates income for workers and owners who will then inevitably spend it on something. If goods went unsold, Ricardo argued it was just a temporary mismatch in pricing, not a systemic failure of the market. Protectionism vs. free trade. The biggest political fight of their lives was over Britain's foreign laws, which placed high tariffs on imported grain to protect domestic agriculture. Malthus defended the tariffs. He argued that Britain needed to be agriculturally self-sufficient in case of war. He also believed that wealthy landlords who made money from these tariffs spent their wealth on luxury goods and servants, which kept the economy moving and prevented the goods he feared. Ricardo despised the tariffs. Armed with his theory of comparative advantage, he argued that forcing Britain to grow its own expensive grain instead of importing cheap Polish or French grain was an enormous waste of resources. He argued that tariffs only served to line the pockets of lazy landlords while shrinking the profits of industrial factory owners, the very people who actually reinvested money to grow the economy. Methodology. Intuition vs. pure logic. Malthus used an inductive approach. He looked at real-world data, history, and human behavior, arguing that economic laws had to adapt to messy human realities. Ricardo used a deductive approach. He built abstract, highly logical mental models based on a few unbreakable assumptions, like opportunity cost. He famously accused Malthus of getting bogged down in minor details rather than looking at overarching principles. This friction birthed the term the Ricardian vice, which modern economists use to describe the habit of using flawless mathematical models that ignore how the real world actually functions. Here I would also like to say, if you are a very good mathematician, it's not necessary that you will be also a very good economist, because in economy, I think you need this intuition to understand how the markets and everything work, because it's also a lot of human interaction, psychology, and unpredictability, of course. Okay, who won the debate? In the short run, Ricardo won completely. His ideas captured the British imagination, leading to a repeal of the Corn Laws and anchoring Western economics to free trade capitalism for a century. Malthus was largely dismissed by mainstream economists as a misguided contrarian. However, in the long run, Malthus got his revenge. In the 1930s, during the Great Depression, the legendary economists John Maynard Keynes realized that Say's law and Ricardo's model couldn't explain why the global economy had collapsed. Keynes looked back at history and resurrected Malthus' ideas on goods and underconsumption to create modern macroeconomics, proving that sometimes an economy can produce more than society is willing to buy. Thomas Malthus published an essay on the principle of population, introducing one of the most famous and grim predictions in history. He argued that humanity was trapped in a perpetual cycle of growth and collapse, meaning that wide-scale poverty, famine, and misery were completely unavoidable. His core argument boiled down to a simple mathematical mismatch between how fast humans multiply versus how fast we can produce food. Malthus viewed land as a fixed resource with rigid limits. He could not foresee the staggering leaps in agricultural technology. The invention of mechanized tractors, synthetic fertilizers, specifically the Haber-Bosch process, which extracts nitrogen from air to fertilize crops, and genetically optimized seeds allows food production to grow exponentially, completely obliterating his arithmetic limit. Today, the world produces more than enough food to feed its billions. As countries industrialize and grow wealthier, infant mortality rates drop, urbanization increases, and women gain greater access to education and career opportunities. Consequently, birth rates collapse. This phenomenon, known as the demographic transition, means that highly developed nations are now facing the exact opposite problem Malthus feared: shrinking aging populations rather than uncontrollable population explosions. The modern perspective, neo-Malthusians, while Malthus was wrong about a global food famine, his underlying warning about resource limits hasn't completely vanished. Modern environmental economists argue that while we bypass the food trap, we are hitting new planetary boundaries, such as carbon emissions, freshwater depletion, and biodiversity loss. The trap wasn't broken, it was just pushed down the road. Behind the dense mathematical economic models David Ricardo is famous for lies a sweeping, scandalous, and incredibly dramatic love story that defined the trajectory of his entire life, casting him out of a wealthy family and forcing him to become the self-made financial prodigy we know today. Realizing their families would never agree to marriage between David and Priscilla, they married in secret. Cut off from both the Jewish and Quaker communities, the young couple had to forge their own spiritual path. They eventually attached themselves to the Unitarian Church, which appealed to David because it valued reason, toleration, and intellectual freedom over religious dogma. Driven by the need to support his new wife, Ricardo completely out-earned his father, amassing a massive fortune that eventually allowed him to retire early and study economics as a hobby. David and Priscilla's marriage was incredibly stable, long-lasting, and happy. They went on to have 8 children, 3 sons and 5 daughters, and eventually purchased a beautiful country estate called Gatecombe Park. While traveling to the town of Bath, specifically to help Priscilla recover from an illness, David walked into a library and picked up Adam Smith's The Wealth of Nations to pass the time. If it weren't for that trip with his wife, he may never have discovered economics at all. When he died, Priscilla was devastated. She lived to the ripe age of 80, keeping his legacy alive. It was a partnership that ended up shaping modern global capitalism. So, Ricardo invented absolute and comparative advantage, and let me read you what was my discussion with AI. Absolute advantage. You can produce more of a good using the same amount of resources as someone else. You are better or faster. Comparative advantage. You can produce a good by sacrificing less of other goods. First populated by economist David Ricardo in 1817. Opportunity cost. is the value of the next best alternative you give up when you make a choice. Opportunity cost is the same as return of the best foregone option, return of the chosen option. Humans have a natural cognitive bias called scarcity mindlessness. We focus on what we are actively buying or doing, completely forgetting about the invisible alternatives. The gym membership trap. You lose $50 to pay for gym where you never went. You say, I lost only $50, but forget what else could you get for that $50. So, what is all about? We have Johnny and Derek, and they're both producing mushrooms and whiskey. I don't know, I chose this because it sounds more interesting to me than to do this. And here we have Kurtz. They have just so much time, so much resources, so much workers, that in one day, Johnny will be green, can make either 4 mushrooms or 3 liters or gallons of whiskey, or anything in between. So this is the line of Johnny. And then we have Derek, and Derek can make 5 mushrooms, 5 kilo mushrooms, or 7 liters of whiskey in that day. Or again, anything in between. So what we see here is that Derek has absolute advantage. He's better at making mushrooms, and he's even better at making whiskey. And now, let's say both are working in 50-50 capacity. So Johnny works 2 mushrooms and 1.5 liter whiskey, and Derek works 3.5 liter whiskey and 2.5 mushrooms. And now we ask ourselves if we can increase that production. And yes, we can say Johnny works only mushrooms, we get 4 mushrooms, and Derek makes only whiskey, we get 7 liters of whiskey. And by the way, this average is, if you combine both, so 1.5 and 3.5 is 5, this circle, and mushrooms together are 4.5 if they are working on average. So, yes, but Johnny says, no, I would like to increase mushrooms, so that they will increase both, even mushrooms and whiskey for the same percentage. And we ask ourselves if we can do this, and of course the answer is yes, we can do it, and we will see how in the moment. So Johnny can make 3 quarters of 0.75, 1 mushroom costs 0.75 whiskey, or 1 whiskey costs 1.33 mushrooms. So we see here on the graph that Johnny is simply better at making mushrooms, he can make more mushrooms, and Derek is better at producing whiskey. So our first logical assumption would be that Johnny should make only mushrooms, and Derek should make mushrooms and whiskey. And we would like to calculate that, and it will turn out that it changes here from this circle to cross, and from here from circle to cross for approximately the same amount. We will calculate it later, but so that keep this picture in mind. You can go backwards, of course. And what would be comparative advantage if Derek would be like this and Johnny like this? Here we would see simply that Johnny should make only mushrooms and Derek only whiskey, and this would be the optimum. Here is the same. But if Johnny and Derek would have parallel lines, then there would be no comparative advantage, only absolute advantage. So all these calculations in that case would be useless. So let's continue. This is just simple calculation. We say that we split Derek's time, Derek splits time, and 1 is 1% of time, so Derek mushrooms, Derek plus Derek whiskey, percentage is the same as 1. And total mushrooms is 4 plus 4 is from Johnny, plus 5 and percentage of Derek mushrooms, and time for whiskey is 0 from Johnny, plus 7 times this percentage of whiskey for Derek. And total produced is 4.5, which we had before. This was combined production at 50% each, 50-50, and times 1 plus P. And P is this increase in percentage. And whiskey is 5 times 1 plus the same. We are seeking for the same increase of percentage for both, for whiskey and for mushrooms. And simple equations, we divide time mushrooms time whiskey and equate with this one. So we get this, we express their mushrooms, we get 0.2, so their weight is 1 minus this is 0.8, and total combined production, final mushrooms is 4 of Johnny plus 5, their mushrooms times 0.2 is 5, and for whiskey we get 5.6. What this means, we increase production from 4.5 from both before to 5, or from 5 to 5.6 for whiskey. And percentage, you calculate this, of course, is the same, 11.5%. So what this tells us? This tells us that in countries, we don't know exactly which has comparative advantage. We know just approximately. If someone doesn't have a climate for raising exotic fruit, ananas, then it's very low advantage. And if someone has not expensive labor force, then it's much better comparative advantage to produce goods where you need a lot of labor force. And this tells us that if countries specialize in certain products where they have comparative advantage, is good for the whole world. Even if some country has absolute advantage, if they will cooperate with country that has comparative advantage, they can both benefit from that. And that is the idea. That is why it's very good that we as a world, that we cooperate with one another and we have more products and more everything. But of course, some products are important for national security or otherwise, so these products should be made as well, not according to this. And of course, probably you asked the same question as I did. Why did we have more products and more people? But in this case, for example, if we have 3 products, we add cocaine, then we will have 3-dimensional graph and the line will become a plane. 3-dimensional plane for one person, and we can have as many persons as we want, and actually as many products if we want. So here we can form a matrix: Johnny, Derek, Tom, Alice, Simone, whiskey, mushrooms, cocaine, beer, and we get a matrix of these times. And there are different approaches to solve this. One is the greedy algorithm, but it's not good because greedy algorithm just picks the currently the best options and it doesn't go back to history, although it's very fast, but greedy would just pick the best comparative advantage from each person. So I was trying something, but it wasn't good, it didn't work out. So in this case, you need to use a linear programming and the so-called simplex algorithm. And this algorithm works in a multi-dimensional space. And it actually searches, if you have more lines that intersect, it searches the vertex that is the most distant. So this is then the optimum. But for simplex algorithm, we will need to know more of Tensor Algebra. But I think in the future, sometimes we will develop this. But as I said before, we actually don't know exactly how much comparative advantage one has. And it can come to a new technology and this comparative advantage will change. So it's questionable if it's useful to calculate precisely how many each has. This is just for intuition, and for that this Ricardo model for today was enough. But now we will continue with Tensor Algebra to finally solve the system of linear equations. So, welcome to Tensor Algebra 5, and the very important equation AX is B. A is matrix, the other two are vectors, and these equations are massively solved all around the world. And these matrices can be million times million or even more matrices. We get, when we have partial differential equations, we discretize them and we put them in this form. So when we are calculating fluids or solids, there are all the time these matrices that we're calculating, and we need to solve this. And even in AI, we're solving this. And the simple one is just to multiply from both sides with inverse matrix. So get x inverse matrix times B. That is one form of solution, but this will come later, not today, because it's quite difficult to calculate inverse, not that difficult. And for that purpose, we have direct methods, and direct methods are exact, are accurate. And we have also iterative methods, because if we have million times million metrics to calculate with direct methods, it would last a long time. Maybe it's not even feasible. So we have iterative methods, and in the iterative methods you guess first the matrix and then you approach to the solution, and then you check the graph. If solution converges, the graph goes down. It diverges, it goes up. But usually it converges, but it can happen that it doesn't find the solution. So this will be pretty main topic in Tensor Algebra. But today we would like to check the Gauss elimination. Gauss, prominent mathematician, German. And what he did is very simple. Here we have 2 times 2 matrix, vector, and he multiplied the first row with A21 divided by A11. So all this you multiply and then subtract from the first from the second equation. And when you do this, you get this, the same as this, and you express here x2, you get this, and from either one of the equation, you get x1, and this is the result. It looks quite complicated, but when we will see now example with numbers, it's really not that difficult. It's every procedure. Here we have our example with numbers. It will be much clearer. Here, A is this, B is this, and we form the so-called augmented matrix, where we just put the line here and we add vector B in the last column. And there are 3 elementary row operations. Interchanging any of 2 rows, it doesn't change the result. Multiplying any row by a scalar which is not 0 or infinity, and adding a multiple of a row to another row, it doesn't change the result. And what we do, row 2 is row 2 minus 2 times row 1, and row 3 is row 3 plus row 1, and we get here 2 zeros you see in the first column. This is first step. What we do then, row 2 is 1/3 of row 2, and row 3 is row 3 minus row 2, and we get this, the so-called row echelon form. And here 4 minus 4, we could divide this by 4, and we will get 1 and minus 1 here at the end. And these numbers are whole numbers, but they could be anything. They could be even complex numbers or another matrices, as we saw before. And from this row echelon form, we can see we have here zeros. They mean that the third x3 is minus 1. You see here x3, and then you go up, you put this value, you get x2, and you get x1, and the result is this vector x. And now Gauss-Jordan elimination method is simply, if we just continue the previous example, and we do the following substitution, row 2 plus row 3, row 1 minus row 3 for row 1, and so on, you just get this identity matrix here. You see one from the main diagonals, or the others are 0, and you get here the solution as well. But computationally, to program this is slower than just Gauss method, but will be maybe important later. And now we have 2 more examples. If you do the same procedure, Gauss method with this matrix, you get the following system, which says here we get all zeros and 3, which says 0 is 3, and that means that there is no solutions, inconsistent system. Or you can get from this matrix all 0 in the last row, and that means that there are infinite solutions. And we saw this in the previous lecture when we were drawing those planes, how they are intersecting by one another. And here you can use AI. I tried and said give me example program, write 3 times 3 matrices and solve the system and show how the planes are intersecting among themselves and give all the examples, and it will do it for you just however you want. It's just to have a very good, very capable programmer, and it can do in any language you want. I needed to change the classroom. They have at 8 o'clock in the evening something. But this is how they do that. Doing my work heavy. Anyway, you will have a program for Gauss elimination to solve any matrix which you like. And this program, it takes random matrix, it gives you to choose what size of this matrix is, and it uses Gauss elimination with pivoting. And first, rank of the matrix is actually, when you get the echelon form, if everything is good, that it has solution, the rank is the same as n. If you have n times n matrix, the rank is the same as n. But if one is missing or more, so that means that rank of matrix A is less than the rank of this augmented matrix A and B, then there is no solution. Says 0 is free. You see that the ranks are different from augmented. And if the rank of A is the same as the rank of augmented matrix, but is less than n, then it has infinite solutions. So if one line was empty, always all zeros. And the other case, if rank is the same of augmented matrix and the matrix and is equal to n, we have unique solution, one solution. So for example, if you have 3 times 2 matrix and vector 3, you calculate it like this, you see here rank is 2 because the last one is 0, and rank 2 is the same of A and is the same of augmented matrix. So it simply has solution is 1 and 2. So the last equation has no sense, no meaning. And the same is used in a program. We use forward elimination with pivoting, scanning current column J from the current row I to find maximum absolute value. We need to find this because if the value is approaching to 0, computer can have problems and you cannot get solution. Unique pivot, and it repeats the scan. Then you have row interchanging, swapping, entire rows are changed. This places dynamical optimum into pivot position. Row elimination, you get multiplying factor, the elements row are multiplying with F and subtracted from row R. And then you get the row echelon form, and you check for these ranks to see how many solutions it has. You will see in program. And finally, you get back substitution, and xi, let me write, is vi from this echelon form minus sum, j is I plus 1 to n, ij is j divided by ai, and I is n minus 1, n minus 2, so on to 1. I suggest you to study this program, to understand it, what each thing does, and if you don't understand it, you can always ask AI, you can paste the program inside AI, and it will explain to you everything. Now what's this? Sometimes we have the case that only vector b is changing, in equation ix is b, only vector b is changing, and we would like to use the same result much faster as if we each time perform Gauss optimization, elimination, excuse me. So for that purpose we form LU. L is lower triangular matrix and U is upper triangular matrix. And U matrix looks like this. You see from main diagonal down we have only zeros and we have elements only here. and then u times x is some vector c. Here ux is c, and L matrix is lower. It has on main diagonal only ones, here on other only zeros, and here it is. And the point of this is pretty much simple. We write LU, the product of these two matrices is A, and L times vector C is vector B. So this LUX minus C is LUX minus LC, which is the same as AX minus B. And here we have the whole procedure for the program which you have there, so it will be easy to understand. And first, multiply first row of L by all columns of U. U1j is A1j, j is 1 to n. Second through nth rows of L multiplied by the first column of U, and you get Li1. Here I is from 2 to n. 3. Process is repeated by multiplying second row of L by the second through n columns of U. U2j is A2j minus L21 times U1j. This is a component form, you see each component of the matrix or vector. 4. The third through nth rows of L are multiplied by the second column of U. And here, from here you get Li2. I is 3 to n, and before j was from 2 to n. 5. In general, the ith row of L is multiplied by the ith through nth columns of U. Uij is Aij minus sum from k is 1 to I minus 1, Lik Ukj. And j is from I plus 1, so on to n. 6. The I plus 1 through nth rows of L are multiplied by the ith columns of U. Lk A is this, Ik A, j is 1, so on, k is A plus 1, A plus 2 to n. And we have more steps. Okay? Here is step 7. For the nth row of L, its coefficients are multiplied by the nth column of U from which U and n is obtained. And U and n is A and n minus this sum. Okay? And the substitution step 8, vector C is obtained with forward substitution. C1 is B1 and Ci is this Bi minus this sum, where I goes from 2 to n. And Bx is found with back substitution. Xn is Cn divided by U and n, and Xi is this, where I goes from n minus 1, n minus 2, so on to 1. And now let's do one example. Here is 4 times 4 matrix A and vector B, and we would like to find the result with LU decomposition. Well, here are all the steps. You just go through this. You get U11, U12, so on, and the second step, Li1, you get 3 L's here, 3 U2j, A2j. I hope it's visible that you can read by yourself, so I won't even explain. Just go through this procedure and you will get all the components of L and U. And here it was less space, so the step 7 is here. You go to this and you will get the matrices. Collecting all the components into the matrices, you will get L like this and U like that, and then LC is B, and you get the vector C. And here, if you get a different result B, this is the same, L and C are the same, L is the same, and you will get another C. And then you will see from this equation, you will get X. Well, the LU composition was good, but of course we have always problems with computers. In some cases it doesn't work. If the number is close to 0, it won't work, so that's why they upgraded it to PLU algorithm. And we just simply introduce a matrix P, which is identity matrix at the beginning, and then when we swapping the rows, we are also swapping this permutation matrix, and it changes so that it kind of remembers the positions, because we need them not like in Gauss elimination. So PA is the same as LU, PAX is P times B, and from this LUX is PB and is some vector D. And if we go to the same problem as we had before, we swap 1 and 4 because the 4 has the largest number, that is 3, and the matrix now U looks like this. We swap those elements and we perform Gauss elimination. I mean, here we get zeros, and then we swap it again 2 with 3 because we see here 2 is the biggest, and it just swaps and put it on here in this place because now we are looking at this part of the matrix only. And finally, you will get the permuted matrix that looks like this. It could be different random. And U and L, the same procedure, you will get as it's written. So then you will calculate vector D as P times B. You will get this, then with forward elimination you will get C from this equation, and with backward you will get X from this equation. And you will see the program, check it, try to understand it every step, and try to change the number, the matrix. It should work for any matrix you will choose. And about floats, the time that computer solves this, you can actually give in a program that it gives you the time, how much it needed to calculate. In Gauss elimination, 2/3 n to the power of 3 plus n squared is this fast, and Gauss Jordan is n to the power of 3, so it's the slowest. This one is better. And LU, PLU is actually the same as Gauss for the first time, but then when you calculate with new B, it's only n squared. So this is it for today. I hope you like it, that it was useful, and see you soon. Thank you. Here we have a butterfly and an ant. He is preparing to take off. Maybe we give a little boost. Kitty is here. Playful kitty, 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 kitty. Oh, orange. Kitty, you're so playful. Yes. Good. Nice one. Beautiful. Kitty would like to play. Kitty, 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 kitty. She's pouring. Come on, pour. I think she likes me. Kitty! Oh my God, you're here! Kitty, you want energy? Kitty, kitty, my love. So beautiful, kitty. So beautiful, kitty. Na 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 na. Kitty, 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 kitty. Now she's looking for something else. I really like her. Good position. She's smelling something. If there was another animal. And some art.